Can you? Wonderful, that's grand. So let's give a very warm welcome again to Ivan Butygin from Intel, who's going to give us a presentation today about the Numba-MLIR project. Ivan, take it away.
Okay, let me check if Dita here. He's not here, but yeah, anyway, let me share my screen. Can you see my screen?
Yes.
Yes, we can see your screen.
So okay, so we want to present our work on Numba-MLIR project, which is basically a Python compiler based on Numba and MLIR infrastructures. We are working on it like for some time already, and we have some progress and interesting insights we can share. So in general, like this is just a Python JIT compiler, same as Numba. It has some same API and programming model as Numba when you basically wrap Python functions with decorator, and on first call to this decorator, those functions are compiled to native code. And we are using Numba frontend and Numba type inference as part of our pipeline, but the rest of the pipeline and like entire layering to the machine code is handled by MLIR infrastructure. So we have working code generation for CPUs and GPUs. We have NumPy parallelization and offload to GPUs. So on CPUs, we are compile it using LLVM and parallelize it using TBB. And for GPU, we compile it to the SPIR-V and offload like through SQL runtime. Also, we have a CUDA-JIT like kernel APIs for GPU, which basically provide the similar API, or conceptually similar API, but it follows more OpenCL style plugin API like get global ID and such. But so why exactly do you want to use MLIR infrastructure? MLIR itself already have a lot of dialects, which is basically custom IRs for the different domains and different like abstraction levels. So, and our goal is like we can benefit from reusing those IRs, those dialects between different devices and between different, like in MLIR there are dialects for CPUs, like for GPUs on different abstraction levels. There are like general GPU dialects, there are NVIDIA dialects, there are SPIR-V dialects and such. And we also want to reuse MLIR code between different MLIR projects. And for example, in MLIR, there are dialects like linalg, which is mostly originated from the machine, from deep learning background, from convolutions and things like that. But actually, a lot of NumPy functions in like map pretty neatly to this linalg dialect, and we want to reuse it, and we want to reuse optimizations from this linalg dialect. There are, as I mentioned, there are GPU dialects and GPU lowering for different vendors. There are loop optimizations like fusion, loop tiling, and so on. And also, we are developing a few of our own dialects, and there are like we can potentially reuse them for different projects, not only like strictly related to Numba or for Python compiler. For example, we have our NumPy dialect, and it can be used. For example, potentially we can build like optimized Gcompiled NumPy-like library, which doesn't like, is not a full compiler, but just like compile individual NumPy functions or like sequence of NumPy functions to the some code. Or there are also some ongoing research work on distributed NumPy, and we would like to cooperate on this front also, on MLIR level. So the current status of the projects, we are supporting most of the we're supporting a lot of Python constructs like Python math, complex numbers, loops, basically arbitrary control flow, like range loops, while loops, and so on. We support some set of NumPy APIs, most of the ufuncs, various indexing modes, broadcasting, which includes support broadcasting for like parallel NumPy and for GPU offloading of NumPy. And also like the set of functions of supported NumPy functions is not that big, but we have our overloading, extending API to add new functions, and it's pretty straightforward to use. So the compiler itself mostly written in C++, but actually implementing new NumPy functions doesn't require any C++ coding or any C++ knowledge actually. So we have support for number per range, parallel loops, and we have, as I mentioned, we have a GPU offloading support. And for now, we are only supporting GPU offloading for the Intel devices, but actually extending it for CUDA should be relatively straightforward. And most of the pipeline will stay unchanged for CUDA comparing to Intel. Okay, so here's some example, and it's basically it looks like and it works like exactly like Numba. You just need to replace Numba and JIT decorator with Numba-MLIR and JIT, and it should work the same. So here's an example with NumPy functions and with prange. Okay, so from probably any questions so far? Okay, so from the implementation point of view, basically our Numba-MLIR and JIT decorator is just wrapper around existing Numba and JIT decorator, but with custom pipeline. So basically, and what we are doing, we are still using Numba type inference, but we replacing all passes after type inference with our custom pass, which is basically from Numba point of view. This is a single pass, but inside it runs entire MLIR pipeline, and it runs entire MLIR pipeline, then convert MLIR code to the LLVM and compile this LLVM to native using org.jit, and then return back just like pointer to the compiled function. And then we have a hacked number layering passes which can understand this, like which can take this function pointer and then plug it into the rest of the Numba infrastructure and call it. So some time ago, we have a slightly different model when we compile to the LLVM and then serialize this LLVM to bitcode and pass it back to Numba. And Numba will compile this LLVM on outside. But like after this, there was a recent switch in LLVM to thing called APEC pointers, which broke LLVM bitcode backward compatibility, and it's no longer working for us because number is only LLVM 14 for now, and we are based on LLVM head. Basically, we are updating every couple of weeks to the head of LLVM main. Okay, so the MLIR pipeline looks like that. We have a Numba-MLIR as input. Actually, I'm not sure. Can you see my mouse?
Yes, we can.
Okay. So we have Numba-MLIR as input, which is like Python Numba-MLIR Python API. And as a first step, we are converting it to the MLIR dialect called Plier. Well, don't ask me why it's called Plier. It's for historical reasons. But basically, Plier dialect is just one-to-one mapping of the Numba-MLIR to the MLIR length. Previously, we were considering doing some optimizations on Plier dialect, but now it's just entirely front-end dialect, and we are converting it almost immediately to some lower-level dialects. Specifically for NumPy, we have an N-tensor dialect, which is our custom dialect, and we are doing optimizations on this level and leveraging like our error loads on this level. And then we convert N-tensor dialect to the Linux dialect, which is upstream dialect, and we reuse optimizations from upstream on Linux, specifically fusion of Linux operations. And then we convert everything to the dialect called SCF, which is start create control flow. And there is another line, basically for non-NumPy code, when let's say if you have explicitly written p-range, we are converting it directly to SCF, skipping the N-tensor and Linux step. And we have a set of passes on SCF level, optimization passes on SCF level as well. We have another round of loop fusion, which works explicitly on loops. So it's probably less powerful than Linux fusion on one hand. On the other hand, like there are some cases which we cannot actually fuse on Linux level, but can fuse on SCF level. So and then after SCF, all optimization SCF is done. Basically, we are splitting depending if you are leveraging code to the host or to GPU. So on the host, we are converting it to the LLVM dialect, which we will also just convert to the usual LLVM and compile it using org.jit. And for the GPU dialect, for the GPU path, we are generating GPU dialect, which is mostly upstream dialect, but we have a few extensions to it, like for our needs. But we plan to upstream most of the changes, like at least on the right side and on SCF side, we are plan to upstream most changes to the MLIR itself. So ideally, like this should be like entire upstream and MLIR dialects without any number specific things. So yeah, on GPU path for our pipeline, we are generating SPIR-V dialects from GPU and converting them to the usual SPIR-V and then lowering it using layer 0 or SQL runtimes. Like layer 0 is the Intel low-level GPU programming API. So sort of close to, let's say, Vulkan probably, but sort of mix of OpenCL and such. And we don't support, as I mentioned, we don't support CUDA-CodeGen yet, but it should be straightforward. So we can, instead of generating Spirit dialect from GPU dialect, we can generate NVGPU dialect, which is upstream dialect, and then convert it to PTX and then compile it using CUDA runtime. And the result is just host function pointer. So for the GPU CodeGen, we are generating small host code, which basically we just create devices and loads kernels and then launches these kernels. So the end result is still a host pointer, which can be called from the number side. Okay, any questions? Okay, so one interesting example when we have benefits of the MLIR infrastructure. So consider the following example, when we have a simple function which just adds to NumPy arrays and return result. But we need to broadcast these arrays. Basically, one of the input arrays dimensions are 1. So we need to broadcast. But this code doesn't work in current number. This is parallel true. But for our compiler, we were able to actually make it work, and we have our specific MLIR pass, which not only make it works functionally correct, but also make it works efficient. And basically, there wasn't obviously this exact pass in upstream, but we were able to reuse a set of existing upstream infrastructure for our broadcasting optimization paths, like array shape propagation, like integer range, which propagates static shapes. So if you can deduce some shapes of your arrays as a static, and this information can be propagated through the code, like integer range analysis, when we propagate range information through the arithmetic hooks, like constant folding, control flow simplifications. And basically, we were able to use this infrastructure without any changes and just take it and you use it. And we don't need to re-implement it on number side. And our implementations work on both on CPU and GPU, and also it is actually like quite isolated from the number or NumPy implementation details. So potentially we can, like, it operates on abstract arrays and such. So potentially we can even upstream it to the core MLIR. Okay, so a few words about our new overload API. So the reason why we needed like different overload API from that Numba already has is that we want to emit more high-level operations than existing Numba API. For example, we want to emit directly. Current Numba API is overload API is, let's say, low level. It just loops and external calls. But for our needs, like to be able to do like high-level optimizations, we want to emit high-level dialects like linalc. So, but as we are still rely on Numba for type inference, we still need existing Numba overloads to do type inference, and that's basically a funny situation. Like we need Numba overloads to do a type inference, but we don't use actual overload Numba provide for code generation. So even like our new API is like intended to emit high-level Linalc primitives, but it still supports if you cannot represent some operations in Linalc, and there are actually quite some operations which cannot be represented, like sorting in Linalc. It still can call arbitrary native functions, external functions from libraries, and it can inline code, like basically any chunk of Python code, including code which do, let's say, p-range calls or NumPy calls itself. So the only limitations that you shouldn't call NumPy function you're overloading, like you're implementing. Okay, so here's a overload example. It's like simplified. I dropped most of the like checks. Hello?
Yes, we can hear you.
Sorry, my headset decided to give me. Hello?
Yeah.
Yeah, okay. So here's an example of overload. So basically for 2D version of NumPy dot. And basically the main thing is this Linalc generic call, which is basically an abstraction on high-level abstraction on nested loops. Basically, we are describing a loop count. So we want 2 parallel loops, V1 and 1 reduction loop. We are describing how to map from the loop iteration indices to the arrays, arrays access. So we have 3 nested loops. We want them, and we have 2-dimensional inputs and outputs. So we want to access them in such way. And then we are just writing a body, which is function which describes a single iteration of this loop. Basically, we have 2 elements which is accessed according to those access mapping, and we are returning a new value which will be deduced, and in the end we are returning the result. Okay, another interesting thing we have. So the current compiler I described. So it basically compiles, it replaces the entire Numba pipeline. But we have another POC which works differently, and instead of compile entire function wrapped in decorator, it just compile specific par4 nodes. So it's sort of like it simplifies things because we don't need any front end, we don't need custom overloads, but we still can utilize MLIR based leveraging for GPU or for TBB if you want. So, and this is also have an advantage that it can be plugged in into existing pipelines, like with minimal changes, but high-level optimizations like fusion are still handled by existing Numba and parallel accelerator. Okay, so few words about how we can potentially cooperate with existing work with which is happens in Numba, or how we can unify our work. So there is a sorry, there is an ongoing work with like ongoing refactoring with Numba frontend, which ports it to RV SDG. And we do not. It is not directly related to MLIR, but it is actually simplifies things for us, because current Numba frontend returns operates on current Numba-MLIR operates on control flow graph with basically random jumps and basic blocks. And in our pipeline, we are using a thing called structured control flow, and we have our custom path which converts from Numba control flow graph to structured control flow. And actually, Numba, after front-end redesign, it will be handled completely on front-end side, and we won't need this custom path. Also, there are potential other incremental other ways to incremental integrations with Numba. For example, instead of running entire pipeline in MLIR, we can try to offload individual passes to MLIR, something like we did for PAR4, PAR4 nodes lowering. But we can do sort of round trip from Numba-MLIR to MLIR, do some optimizations on MLIR side and convert it back to Numba-MLIR. We didn't decided yet if we really want to go this way, and if there is actual opportunities to do this, but this one thing to consider. And also about redesign overload API. So we can't use existing Numba overload API, but the opposite is the opposite direction is possible, because we are leveraging our we're leveraging our overload API to high-level Linux operations, but actually, I think it is possible to just lever it directly to the loops and skip completely our MLIR pipeline, but still use our new overloads. And so do a shim between Numba-MLIR and Numba overloads. So new NumPy functions can be implemented using this new overload API without actually immediately porting entire pipeline to MLIR. Probably directly using our new overload API is not good. It's not ideal, because we have some MLIR conventions, let's say, baked in, but we can think of discussing a general high-level API for things like Linux, ops and such. Okay, and this is actually the last real slide. So our project is on GitHub. You can check it out, and we also have we are uploading development builds to the development channel. This is basically just, we don't have proper releases yet, but this is just automatically uploaded from successful CI runs. So you can just install it using Conda and try it out with minimum effort. Okay, and that's all. So any questions?
Do you have any benchmarks that show performance differences, say for the CPU?
We we had, I don't have exact numbers on hand. We had some benchmarks. We had some benchmarks in the past, and we have some performance improvement compared to the existing number. On some workloads, we were on par with existing number or some other workloads. So basically, we were either faster or at least not slower.
Also, do you know what sort of an impact the new pipeline has? Is it slower? Is it faster in terms of generating code?
Specifically for compilation speed, we didn't actually measure it. Like I would expect it will be faster because it's most of the pipeline written in C++, most of the passes written in C++, but we didn't do actual measurements, and it wasn't our it is entirely possible that I did something stupid and it's actually slower than existing.
Ivan, I think you also have a. Is it this week that you will have a MLIR?
Yeah, I forgot to mention. So this Thursday will be a MLIR open forum where I will be discussing actually low-level implementation details on our MLIR pipeline. So it's public, so anyone can attend. But it will be really low-level details, and it will probably require some prior MLIR knowledge.
So, will you be talking more about the N-tensor dialect and the Pylar dialects there?
So, well, I'm planning to mostly discuss N-tensor dialect and also our GPU layering pipeline.
Okay. Yeah, so I probably want to know more about the dialects themselves. I will save questions until after the first day presentation on those.
I would like to ask a question.
Okay.
So the question is, so how can I imagine this? So currently, what is sort of let's say, what are the use cases that Numba-MLIR unlocks?
This is mostly for one of the big use cases is this entire GPU offloading for Intel devices, and
but is it also like a drop-in for the Parallel 4 accelerator that we currently have in Numba? Would it be like a drop-in replacement for that?
Yes, it's intended to be a drop-in, basically. Like the long-term goal is to be drop-in replacement for an entire Numba. Let's say currently we do not support all the features Numba supports. We do not support lists or dicts or JIT classes.
Okay.
But for numeric NumPy code, it should work as a drop-in replacement.
So would you agree that the two use cases are offloading to Intel hardware and as a drop-in replacement for the current PAR4 implementation in Numba?
Yeah, and also the one of the issues with current Numba is that basically if you do any optimizations on the Numba-IR, let's say, basically it stays in Numba. You cannot use it in any other projects. but with MLIR we plan to reuse at least the entire GPU lowering pipeline in other project, not directly related to Numba.
Right. So you could,
it's just to
yeah.
it's just to reuse increase the use of code, and reduce the Numba specific.
Right, so you could potentially also emit an MLIR dialect from Numba-MLIR and then use some other programs lowering pipeline, for example, to lower to C code and then to send that to Apple
exactly.
Metal or some other some other companies' custom hardware.
Yes, exactly. So basically,
just one thing to add, Val, on that question. So just one clarification. So the use case, right now the focus definitely is, as far as the architectures go, is on Intel, but this is not being done per se to support just Intel. I want to clarify on that. So one of the goals of using MLIR is to get the portability aspect. So Linalg already supports, actually there's much better support for CUDA GPUs than Intel GPUs at this point. So the goal really is to, if we go to MLIR, we can get that portability, which is inherent in this ecosystem. And so it's nothing specific to Intel at this point. So it's just, we hope that once we are able to get to MLIR, we get much better portability and architecture support.
Okay, that's great. Thank you for mentioning that, Dipto. It's good to know that the targets are also open and that the architecture is open and sort of you've future-proofed it in the sense that you've taken into account potential future use cases and also potential future hardware. That's really nice to hear.
Yeah, and one other thing is, as Ivan was saying, so it is a drop-in replacement of parallel accelerator, or at least an intended drop-in replacement. But there are various things as far as loop optimizations and even loop analysis, which if we have to either implement from scratch inside Numba parallel accelerate the PAR4 infrastructure, or we have to somehow rely on the LVM, for example, the poly optimizer. But these things, at this point, the sense we get is that if we go to MLIR and intercept it at a high level point, let's say the Linalg seems to be more logical at this point. So we would get some of these analysis capabilities and optimized code generation capabilities for free, because the community as a whole is investing in those. So we won't have to do anything specific for Numba, especially talking specifically for the PAR4 parallelization.
Cool, thank you. No, there were some questions in the chat, I believe, as well. I don't know if they've all been answered, Todd. You've been tending to that, I see.
Been giving my opinion. Other people might have different opinions.
Well, I guess Ludger, is there any question you want to ask the speaker from the questions that you asked?
Yeah, sure. Because Motion in a sense also has at some point to go for SCF and Linalg, right? So below that point, is there anything specific to this which would make it different, or are you planning to run any further optimization passes on there which are more specific to the kind of behavior that you usually see in a Numba code?
So, the general idea is that after the SCF stage, all the entire pipeline and all the optimizations still be generic, and we still have some small things specific to Numba on the layering. We have, for example, a reference counted memrefs, for example, to interpret with number arrays, NumPy arrays, but it's really like small, and so yeah, the entire intentions that the most of the pipeline should be as generic as possible and can be so it can be reused between projects.
If you don't mind, I also have some opinion regarding MLIR and Mojo. So one of the kind of thing that I see with using MLIR as a backend, and also something that you've already mentioned, which is related to making the extension API, the overload API, higher level, is that we can actually build up higher level dialects and layers. So on top of kind of SCF, or like even on top of N-tensors. And one library that the Numba team is kind of interested in investigating is called XDSL. They are providing a way for a Pythonic API to define dialects and even transformations on MLIR. And we are interested in pursuing that as a way for people to create kind of higher level abstractions. Like, what if like N-tensor is the dialect that a future NumPy library is written on? Can we then make a NumPy library that automatically targets all the backend here without rewriting it for like CuPy or something else? And if there is a kind of going into kind of fantasy land here, if NumPy itself is more like a dialect, can we apply high-level optimizations, knowing specifically just to the NumPy API semantic? And with XDSL, maybe we can write those optimizations that can be written in pure Python. And we've talked to the XDSL authors, and part of their plan is to leverage MLIR's. They have a dialect extension and dialect, so you can write dialects within a dialect for MLIR, and so that the dialect implemented within Python is actually also usable in the C++ MLIR. So kind of that is what I think we can do within the Python ecosystem.
Yeah, and like I think dynamically defining dialects is a thing which already discussed in like MLIR upstream. I don't know what the current status of it, but at least it's being discussed.
Can you hear me?
Yes.
Now
we can. Yeah.
Yeah, okay, so this is Frank. Yeah, so basically in a sibling project, which is like, Ivan mentioned it briefly before, we were trying to see whether arrays, NumPy-like arrays, can be automatically distributed. We are doing something that, like what you mentioned, we are trying to implement a dialect which resembles the array API. So basically you would have a dialect that is more or less what the array API defines. And then whatever you have in your XDSL could load to that or whatever you want. So that's basically a side project here.
Okay. Any other questions?
Right, that sounds like a no to me. Seems like all of the questions have been answered, and we have a recording. So if anyone wants to go back and revisit different parts of this conversation and presentation, hopefully Sue will have uploaded that to the Numba YouTube channel soon after the meeting. And that concludes the MLIR presentation of our meeting. And yeah, thank you very much, Ivan. It was a really great pleasure to have you here talking about Numba-MLIR. I think we've all learned quite a lot, and now we all go away with lots of food for thought and thinking about exciting new ways to integrate Numba-MLIR and use it and see, you know, what the future holds. So it's an exciting time that's ahead of us. All right, so just to conclude the meeting, is there anyone else who has